Thank you very much to the organizers for inviting me. It's been a lot of fun so far. And I guess I'm one of those people who have been positively impacted by IPAM at various stages of their career. It's always nice to be back. So I will be talking about operator methods for dynamical system, and in particular as they apply to Earth system dynamics. And this is a framework in which was pioneered by people like von Neumann, Koopman, and Berkhoff in the first half of the 20th century. And it involves characterizing aspects of nonlinear dynamics through their induced action on spaces of observables, so quantities that we can measure, or measures. By measures here I mean things like probability distributions. And the key aspect of this characterization is that because these spaces here tend to be linear, we can add together functions that take values on, say, real or complex numbers. We can scale or multiply them. We can do linear operations on them. We can study a nonlinear dynamical flow through its action on such spaces. And it turns out that it acts by means of linear operators. So think of this dynamical flow as the evolution of the climate system or the solution map for your climate model at a certain time t, and this is going to be some type of state space that depends on the application at hand. And within this context, one that typically looks at two types of operators. The first is the composition operator, which is also known as the Koopman operator commonly, and it acts as given by this formula by composition with a dynamical flow. So think of it as a transformation on the space of observables, which takes as an input an observable f, so some quantity of interest, and it turns a new observable such that when you evaluate it, you basically first advance the evaluation point by the dynamics over time t, and then evaluate f. So it kind of like moves forward the observable in time. And the dual of this operator, which is known as a Perron-Frobenius or transfer operator, acts basically on probability or on measures, or for example, probability distributions. And for certain types of dynamical systems, you can characterize it by the inverse of the map. And together, basically, this gives us theoretical, analytical tools to study aspects of nonlinear dynamics through properties of these linear operators. For example, it turns out that you can encode properties like ergodicity and mixing into corresponding properties of the spectra of these operators in appropriately defined function spaces. Another way of thinking about this, since yesterday we heard a talk on representation theory, this is some type of representation theory. We have a group of nonlinear transformations, and we are studying it through its action on linear spaces. This is like a representation theoretic concept fundamentally. So from the point of view of this workshop, I guess, what is of relevance is that in the past, I guess, a couple of decades or more at this point, there has been significant interest in taking this framework and implementing it numerically, in particular with data-driven techniques that take as inputs observables, typically sampled along trajectories, and produce various approximations of these operators to be used for things like feature extraction or statistical modeling of dynamics, which I will talk about later on. These are just a few examptions just for if you want to look into this in more detail in the literature. Some of the early papers were, for instance, on the transfer operator literature by Gary Froiland, who's here in the audience. And there are also related approaches which are relevant for climate dynamics, or I should say Earth system dynamics. And for instance, the linear inverse models, one can think of it as a basic approximation of the Koopman operator in a space of linear observables, and that has been around. And then the DMD, dynamic mode decomposition technique, numerically, if you've heard of that method, turns out to be essentially equivalent limbs. And singular spectrum analysis, Michael has been a pioneer in this area, is also broadly related in the sense of being another linear operator technique that seeks to capture coherent dynamics, coherent observables from complex dynamical systems. So I will be talking about methods, as I just mentioned, that are either for feature extraction. You can think of it unsupervised machine learning, where the goal is to discover observables that evolve in a nice or predictable way from under complex dynamics, or in a supervised learning context that will be for predictive modeling for tasks like data assimilation or closure. So what I'm hoping to do is kind of like give a few vignettes, if you wish, of these aspects in the time that I have, just as a showcase of the type of things that one can do with this methodology. And I think later in the week, Gary's and Claire's talks will be like in a related, broadly related area as well. So from the point of view of the pipeline, the methods are relatively similar to other machine learning or sort of like principal component analysis type techniques. We have as inputs spatial and temporal data, like observed climate variables, and we use these to build approximations of the operator at hand and use them in different ways depending on the task that we have. So I should say also, please interrupt me at any point if I say something that is not clear or for any other questions. Okay, so let me start from just before I tell you more about how to actually compute this in more detail, let me show you here as an illustration the kind of things that you can do with these spectral decompositions of this operator. So this is from a joint paper with Gary, where we took here a data set that consists from trajectory data from the Lorentz 63 system. And we want to compare here in this movie, like one of the evolution of the features extracted by the principal components analysis technique. This is like a vanilla data processing or dimension reduction technique. It's basically equivalent to empirical orthogonal function analysis in the climate science literature. So we want to compare the results from this feature extraction method with one of the eigenfunctions that one obtains from approximations of the Koopman or transfer operator. And we want to think of the results of either of these methods, PCA or Koopman operator again decomposition, as defining some type of observable on the Lorentz 63 system, attractor. So in this case, in the top row, I'm showing the results from PCA. So by the colors here, we're coloring the values of the first principal component. So that's like the maximally explanatory from the point of view of variance component on the Lorentz attractor. And because essentially PCA involves taking, in this case, like a 3x3 covariance matrix, computing its eigen decomposition and projecting onto the eigenvectors, we get a linear dependence on the state vector. And so you see here like a linear progression of colors from the left to right, basically capturing which lobe of the attractor the state is. And what we're going to show here is how this principal component evolves when it's sampled along a dynamical trajectory. In fact, here we're going to show the leading two principal components in a two-dimensional trace plot. And here we're going to see a time series of the first principal component. And we're going to compare it with the corresponding results that one gets from one of the eigenvectors of an approximation of the Koopman or transfer operator for this system. These eigenvectors tend to be, they can be rather complex valued. So here what we're showing is the real part in colors. And here we're showing the complex phase. And in these panels, we're going to follow a similar evolution, as a trace plot on the complex plane of the real and imaginary parts, and a time series of the real part. And so assuming that this here cooperates, let's see. What I want to highlight is that this basically, the evolution of these observables has a rather distinct behavior. So here, we're essentially performing a linear projection. So when we look at these trace plots, if you've seen corresponding data from the Lorentz 63 system, they are qualitatively similar to sort of like this chaotic behavior of the Lorentz 63 time series. In other words, they are as complex in some sense as the original dynamical system. But in contrast, this observable, by the way it's structured on the attractor, when we follow it along a trajectory, it has this much more cyclical evolution. In fact, it remains highly correlated over multiple Lyapunov timescales. So you can have observables even in these chaotic systems that are non-trivial in space, but also have non-trivial correlation times, meaning significantly longer than what you would get or expect from the basis of the state vector alone. And so these methods, you can think of them when applied in this unsupervised learning context as a tool to discover these type of observables from data. So like they were not given information about the equations of motion in the case, although there are versions of the methods that one can inject information from equations of motion. But in this case, they were just given time series and they output these type of patterns. And there is a theoretical understanding as to why this happens. Now, on to a more, like a related, but like a more real world example. This is showing something similar for extracting an index or eigenfunction that represents the Madden-Julian oscillation. This is the corresponding time series obtained from a Koopman eigendecomposition that uses the same data, or the same atmospheric variables as used to define the more conventional RMM index for the MJO that is shown here. So what I want to highlight for this is that you can get this more cyclical and slowly decorrelating and potentially more predictable indices identifying climate phenomena. And this can be useful for a variety, I think, of tasks related to machine learning because, for instance, this could provide a set of features or coordinates through which to compare different models or to compute conditional statistics of observables of models conditioned on these eigenfunctions as indices. So you can recover, for instance, life cycles of OLR or atmospheric winds conditioned on these features. And the hope is that they capture more meaningful, dynamically relevant structures than methods that are based on variance maximization or PCA. Now, the other thing that these methods provide is that they can simultaneously recover multiple, patterns spanning multiple timescales in the spectra, where the eigenvalues can give us information about characteristic timescales of evolution, as well as characteristic decorrelation timescale. So in this example, we took data from a control integration of a climate model, and this is showing a spectrum, numerical spectrum of the so-called Koopman generator. This is an infinitesimal generator of the Koopman group in continuous time. So the details here are not particularly important, but the way to interpret this spectrum is that the imaginary line corresponds to frequency, and the imaginary line is basically growth rate. These are negative values, so these are capturing decay, and you can see that basically it's capturing distinct families of modes having to do with phenomena like the annual cycle, and so decadal variability, and even climate change trends in an observational context. Here, this model doesn't have climate change in the simulation, at least. And I want to highlight that in addition to capturing modes that you would call like the fundamental modes in a cycle, like the El Nino phenomenon, you can capture, and this can be expected theoretically, product modes that can capture the interactions between modes of different primary frequencies. For example, the interaction between ENSO, the El Nino Southern Oscillation, and the seasonal cycle has been of interest in the literature because of mechanistic understanding of ENSO, the ENSO's life cycle and its seasonal and its locking with the seasonal cycle. So I'm going to go through this. Oh, yes, please.
I'm wondering, for the product modes, how does that map back to the eigenfunctions?
Oh.
Since it's two modes.
Yes, I will show you. Actually, that's a great segue. It basically, this is an example of this. This is now from a reanalysis data set where you have, there is actually climate change trends, and these are actual years going from the 70s to the 2000s. And there are eigenfunctions, for example, that have this like a secular-like behavior that one would attribute to climate change trends. And then the product modes of these eigenfunctions with a seasonal cycle are shown here in these blue lines. They basically have like an amplitude modulated structure of amplitude modulated waves. So these would be examples of these product modes. And like in the frequency domain, they have a frequency that basically corresponds to sums of the underlying frequencies. In this case, because the frequency of this trend mode is numerically 0, the frequency doesn't really change. But for example, you could have combination modes between ENSO and the seasonal cycle where the frequency changes. And this can be useful, for instance, if you want to ask questions, how did the seasonal cycle of precipitation, in this example, how did the seasonal cycle of precipitation change as a result of climate change trends, at least as attributed to this by this method? And so you can use these combination modes to build various types of reconstructions and composites. Here we did that over South America and identify how basically the seasonal cycle of precipitation changed as a result of the trend. Again, the take-home message here is that these are providing some type of dynamically relevant, granular level of description that could be used to diagnose both observational reanalysis and model data. So that's sort of like the one of the use cases here. Let me do how I'm doing with time. Okay, so maybe I'll pause for a second in case there are any questions before I slightly switch gears. I'm happy to talk about this offline. But now for the rest of the talk, I want to talk about more like a supervised learning aspects of these methodologies, and starting from data simulation, like how we can formulate like the Bayesian data simulation in this operator language, where interestingly, at least in my view, one could maybe disagree, there are connections between this approach at a mathematical level and the mathematical formalism of a quantum mechanical system that comes from this Koopman operator theory. So let me describe this.
Did you skip a slide with the? You were going to talk about trends when there was a question.
Oh, I was going to, but because I'm running a little bit behind, this was just showing the one of the trend modes that you can get from reanalysis data of SST. The blue color is the actual eigenfunction, and here we're showing how it correlates with surface air temperature or SST anomalies and surface air temperature anomalies. So this was, you could think of it as the fundamental sort of like trend mode identified by this method. And what I was showing here in blue was the combination, the product mode with the trend. Thanks. Okay, so let me just walk you through this. So the idea here is that we have our dynamical system, and now we're interested in how, in data simulation, the natural focus is on how a dynamical system acts on probability distributions. When we heard already talks on data simulation where we have a model that evolves an ensemble of states. What it really does, it's like evolving a probability distribution on state space. And here we're thinking that we have our think of this map here, T, as the solution map for your model over one time step, and how this map acts on probability densities, which are the objects of interest, again, in data simulations through the transfer operator, which is shown here. But as I mentioned here, we're also interested in how it acts on observables. So maybe to give a concrete example, say we're interested in predicting the evolution of SST at a given location. This is the example I will show later on, and this would be an example of an observable when we have some underlying notion of state of knowledge about the state encoded in a probability density. So we want to use these methods, these operator methods, but at least from the point of view like data-driven techniques or numerical techniques, a natural space to work with is basically spaces in which we have tools like inner products, and we can talk about adjoints of operators. These are very useful numerical tools. And so the natural space to work from a numerical standpoint here is this Hilbert space of L2, square integrable functions. Unlike the space of probability densities, which is naturally they live in L1, so integrable as opposed to square integrable. And in fact, the Koopman operator acts as a unitary operator under appropriate assumptions on this space. If you're familiar at all with quantum mechanics, unitary operators are the operators that govern evolutions over there, and the states are actually described by operators acting on a Hilbert space. So what we're going to do is we're going to consider, and I will try to motivate later why that is useful, to consider a mapping of our probability densities into a space of so-called quantum states on our Hilbert space. This may look a little bit wacky, so let me just try to give a kind of like a high-level explanation of what is going on. So if we want to think of like classical probability densities, so these are, you can think of the classical statistical states. Well, what these are, there are like functions that go from our state space to the real numbers. The functions are positive, being probability densities. They're integrable, and they integrate to 1. So if we take the integral of p with respect to our reference measure, that is going to be equal to 1. Now, in quantum theory, you can build basically, quantum theory provides an analogous version of classical statistical theory where all of these objects that you encounter, like probability densities or random variables, they're basically replaced by operators. So if we look at the quantum level of description, so quantum states, I will call it, well, these are also, they are operators. So they are operators, I will call them rho. They're called density operators that act on a Hilbert space. So now these are linear operators on a Hilbert space, but they're operators which are positive in the sense of being positive definite operators. Think of it analogous to the notion of a positive definite matrix. And the analogous condition of integrating to 1 is that they have trace equal to 1. So they're trace class operators that are normalized in this way. And so we can create, was there a question? So we can create essentially a representation of our classical statistical evolution. This is basically where data simulation works in this quantum formalism by taking probability densities, taking their square root. So if you take a probability density, it's a unit vector in L1, it integrates to 1. If you take its square root, you get a unit vector in L2. So the square of the square root is an integral that integrates to 1. You can think of this in analogy with a quantum mechanical wave function. And you can build a density operator, which is effectively a projection operator in this setup that projects along this unit vector. So this rho here, you can describe it how it acts on the Hilbert space. It takes basically the projection of a vector in the Hilbert space along the square root of the density. So think of it as a projection matrix. By the way, a lot of this numerically will boil down to doing matrix algebra with dense matrices, which I was happy to learn from Noah's talk, work well on GPUs. This thing, you can think of it as some type of projection matrix that encodes information about an entire probability distribution. Now, we can do something similar with observables. So there is observables, which are functions classically. We can map them into quantum observables, which are operators. And the way we're going to do that, we're going to define for a classical observable an operator, I'm calling here pi of f, that acts on other observables by multiplication. This, in some loose sense, is like a version of an infinite diagonal matrix. Think of it this way. It's not an exactly precise analogy because of some complications in infinite dimensions related to that, but roughly speaking, this is what happens. And these objects evolve under the rules, basically, of quantum mechanics, under these unitary evolutions. Again, by analogy with finite dimensions, this is an analogous transformation as what you do to rotate a matrix under a change of basis. So this unitary Koopman operator rotates, in some sense, these quantum states unitarily. And this diagram here, or like this representation, is fully consistent with a classical one in the sense of commuting, this commuting diagram. In other words, you can recover your classical expectations as quantum expectations in this setup. Now this, what we've done so far is effectively we've created a copy of our system into this like much larger space of density operators on a Hilbert space. But when we do numerical computations, we're working with finite dimensional approximations of the system, which are basically matrices. So we are encoding information about probabilities and observables. We do the same thing for operators, for quantum observables. We're encoding information not as vectors, but as matrices in this scheme. Our notion, our generalized version of probability densities are going to be these projected density operators. These are finite, positive definite matrices. And similarly, we have projected quantum observables and evolutions on our space of quantum, of finite dimensional quantum states. And the reason I think that this is at least somewhat natural to consider is because of the way projections, which is basically what we're doing when we're creating numerical algorithms, behave in these in spaces of operators as opposed to spaces of function. The fact that we're performing approximations starting from a larger this quantum mechanical state space down to finite dimensions, in a way gives us some possibilities for structure preserving approximations that were not, at least automatically not present when working at the level of functions. And the example that I want to highlight here is that of positivity preservation, which may be important in applications of relevance to climate science, because we have many observables that are sign definite, that we want to respect that, like energy and density and temperature. If you take a positive function, say if you took a classical probability density and you project it orthogonally to a finite dimensional space, it is well known that this operation did not preserve positivity. So for instance, the Gibbs phenomenon is a classical example where you take a top hat function, think of it as the function nu. When you project it onto a finite number of Fourier modes, it can have oscillations to negative values. On the other hand, projecting quantum observables is an automatically positivity preserving operation, because the way it happens is you sandwich the observable from the left and right by projection operators. And from matrix algebra, for instance, in finite dimensions, we know that if you take a positive definite matrix and you multiply it from the left and the right by self-adjoint matrices, the result is still positive. So to me, this is one reason why, when talking about formulating this problem, these statistical problems in Hilbert space settings, which again are ubiquitously used in numerical applications, it is natural to work in terms of these, density matrices and corresponding multiplication operators as a way of encoding information about the original system in a way that preserves features like positivity. Okay. Yes.
It's been a while since I've done this math, so this may be a dumb question, but I think few slides ago you said the system had to have an invariant measure.
Yes.
Does that have a physical implication, like statistically stationary?
Well, we have, so in general, that's a good question. So, and something that's glossed over under the rug sometimes in this literature is in order to define appropriately all these Koopman and transfer operators, the choice of space that you work with is crucial. Now, a generic dynamical system under fairly mild assumptions will have one or more invariant measures. So even the Lorentz 63 system that I was showing initially, it is dissipative when you think of it from the point of view of volume in three-dimensional space, but it does have an invariant probability measure. It's not a smooth measure. It's like think of it as some type of like a delta function or so, which is concentrated on the Lorentz attractor, but it has a rigorously defined invariant measure, and you can do the analysis working in those spaces. It turns out that numerically, when you do sampling along trajectories, the various data-driven approximation that one makes is through time averages along trajectories, which basically end up approximating these invariant measures of your system. So yes, it's a good question. There is an implicit assumption of an invariant measure, but many systems will have it, and many systems you can consider that if you have one trajectory or at your disposal, it will sample some invariant measure. So you could, basically pretend that your method is formulated in that space. But yeah, there are many other possible choices of space besides these L2 spaces. Although invariably, when dealing with numerics, having a Hilbert space structure is very useful. Any other question? Maybe Gary has other opinions about the choice of.
This operator, is it integral preserving as far as being positive?
Not necessarily. It's not it's not necessarily an integral operator at this point. Why would preserving?
In your commutative diagram, P at the top is preserving new integrals.
Oh yeah, it has. Well, you have to normalize it, and then when you normalize it, it has unit trace. So yeah, that's the corresponding. Okay, so let me show. I guess I have about 25 minutes. Let me show how this data simulation works in practice. Basically, it's a literal translation of the Bayesian or Kalman type filtering that you have in classical statistics. You're replacing everything by the quantum mechanical counterparts. Rather, instead of using probability densities, we have a evolution for density operators. Think of this as the forecast step in classical data simulation. And I didn't get to talk about this in detail, but there is an analysis step that one can formulate. There's a quantum version of Bayes' rule that you can condition a quantum state based on what are known as quantum events or quantum effects. So there is an analogous formulation as to Bayesian conditioning, such that when you have a classical system evolving, so think of this as the true state of the system, you're making some observations. There is a way that you can condition the quantum state. I don't have time to go into the details here to basically replace the Bayesian analysis step from classical data assimilation. And when you iterate this process, it basically carries forward an evolution of these density operators that again encode information about the state of the system in a similar vein as classical data simulation. How it works? Well, basically we use samples, as I mentioned, of the various observables, quantities along dynamical trajectories, and I'm happy to talk about this offline. We build approximations of our transfer operators and the operators representing our observables using, in this case, kernel techniques to do this in a manner that is sort of like asymptotically consistent, meaning in the limit of a large training data set. And once we have these matrices, we can basically run data simulation as we would do classically. And what I will highlight here is that this method evolves a quantum state, so it can yield basically probabilistic predictions about arbitrary observables. You can say, so what I'm denoting here, omega here would be, say, an interval. Say I want to find the probability that precipitation will exceed a certain threshold or temperature will be in a certain interval. This would be omega. So the rules of quantum mechanics, and I don't have time to describe this here, they give you a recipe which is similar to how you compute conditional probabilities in classical statistics. To do that with these density matrices. And again, there is this Bayes rule that allows you to condition your quantum state as the system evolves. So you have this iterative conditioning of the state. So as an example, here we have one application where we do data simulation of El Nino. This is done all in a climate model, so it's not, I don't want to overclaim anything here. This is basically, we took a long training data set from a control integration of climate model, and we use observations of Indo-Pacific SST as our observed data to predict the observable would be the Nino 3.4 index, so average SST in this box. And in this diagram, here what I'm showing is like a running forecast for the Nino 3.4 index, where the colors here are basically logarithms of probability density as predicted by this quantum state. So this can give you basically like a fully probabilistic forecast. You can query the state to get, for instance, predictions of the mean, of the variance, here of the probability density for the Nino 3.4 index. And as you expect, like the lead time is going downwards in this diagram. You start from like a rather sharp probability distribution, but then over time, of course, this is going, I think, down to like 9 months. There is increase of uncertainty as you would expect. So it gives you this sort of like intrinsically, it's a numerical method that operates on these deterministic objects, meaning this quantum state vectors, but it can give you probabilistic predictions of observables. Okay. Any other? Yeah.
Like what's the, like, so you had an update rule for the quantum state.
Mm-hmm.
Like how many, what's the shape, like what's the dot shape of the quantum state in this, for this plot?
The shape of the quantum state?
Yeah, like there's something that's being tracked through time.
Yeah, it's a matrix, so it's hard to visualize it, right? It's like it's a matrix. So it's a matrix that is being evolved between Bayesian updates. It's being evolved by the transfer operator. And when you make an observation, you condition it similar to how you go from the prior to the posterior in data simulation. There is an analogous formula that allows you to condition this matrix. And now how do you render predictions? Well, and produce the plots that I made. It's like, say you want to compute the expectation of your observable. Your observable is also represented by a matrix. Here I'm calling it A. Well, that you compute the trace of the state times the matrix. This is analogous to computing the integral of f fp d mu. This is the analog, the classic analog of the quantum analog of the classical expectation. And then Bayes formula has a formula. I can write it down later, but yeah.
Yeah, I just like wondering what numbers actually go into that plot. Like what's actually.
Well, what I'm plotting here to get the lines, I'm plotting the mean. So the thick line was the mean, and the colors are the probabilities for different bins to omega. So that would be the probability that your Nino 3.4 index is between, I don't know, 0.5 and 0.6 Kelvin or something. So there's like omegas here there are different bins, and the colors here are made by evaluating the probability on these bins.
And is it like a two-step process? Like first you realize the matrix and then you take the expected value, or is each observable?
It's a two-step process. It's basically similar to how you would utilize a probability density in classical data simulation. You could utilize it to make forecasts. Let's say I want to predict what is the temperature here like tomorrow or 2 days, but I'm assimilating data every, I don't know how many hours, so I can be conditioning it every few hours and keep making forecasts into the future. So it's basically, structurally it's very similar. You're just changing vectors to matrices in a way.
So what was being assimilated in your experiment?
SST fields, Indo-Pacific, this,
I see the number 300 there. This is the length.
Yes, this is basically what we use for training and for computing the, various forecast skill scores and things. So this is trained on a long free-running climate model. Yeah.
What does training mean?
Training, maybe I'm using that word a bit liberally because this is not deep learning or something. It means this. It means you take the SST snapshots, you use those, maybe this will come out more in Gary's or Claire's talk. You use these snapshots to build a basis for observables. So think of it as doing some type of kernel PCA in this step. And once you have a basis for a finite dimensional Hilbert space, you can represent all of your dynamical evolution operators and your observables as matrices in this basis. I didn't explain here, admittedly, how you do this from the data. Effectively, what you do is like these inner products you represent by empirical means, like in the same way that you compute, say, a loss function from samples. So think of this as like your empirical mean, these brackets.
You have some orthonormal basis. You regress that onto the observable.
Yes.
So in this case, Nino 3.4.
It's not just regression of the observable, it's building this multiplication operator. This contains more information than just regression. But yeah, effectively, it's close. Operationally, it's close to that. Yeah. Yes, please.
Hello. I really like that you can query the map that you showed, and you have the lead time. Can you go to that slide? I think it's the next one. Yep, that one. I was just curious about why is it that as lead time increases, it seems to get a bit more streaky in terms of the.
I think some of this is it's a good question. I think it's because of it happened that maybe at those particular instances, we're doing this Bayesian conditioning. I think here, I forget, it could be every month. And even though we're predicting several months in the future, it could be that in a certain month, I don't know, something may have happened that caused a more rapid change of the state based on the evolution of the model. Some of this is a little bit visual, I think, because these bins here near the top and the bottom, I chose them to have equal probability mass, so near the tails, near the extremes, the bins tend to be larger, so like it looks a little bit more streaky than it really is, I think, on this diagram. Any other questions? Okay, so I guess I have about 10 minutes, 7 minutes. I will then focus on the next part, will be dynamical closure. And that is basically like a closely related setup to what I was describing now for data simulation, but the difference being that now the quantum system is also allowed to influence the classical system, unlike data simulation that we're only observing. Now we're actually like predicting, closure terms and forcing the original system as in a closure problem. This was inspired by this paper of Palmer, who looked at I imagine a number of people are familiar with this paper, of a stochastic closure for the Lorentz 63 equations. His argument being that a deterministic closure for a this like low-dimensional dynamical system, if you were to remove one of the equations of motion, you would end up with a two-dimensional system that cannot exhibit chaos under smooth dynamics in two-dimensional Euclidean space. This is a fundamental result from dynamical systems. But on the other hand, if you do the closure stochastically, so you force the system, you can recover by drawing, I think in this case it was like a Gaussian white noise, you can recover a structure that broadly resembles the Lorentz 63 butterfly. And one way of thinking about this stochastic closure is that the stochastic process itself has a state space. So it's a formally infinite dimensional space of sequences, like where is a Bernoulli shift or so operating. And by doing stochastic closure, one is really augmenting the dimension of the effective dimension of the state space of the system, and they can thus overcome limitations from this Poincaré-Bendixson theorem, as it's called. So what in the 5 minutes that I have, I'll just show you very quickly how the same approach can be done, but now instead of using a classical stochastic process, we're going to use this language where we have our original system, and we want to estimate these xi here are closure terms. I'm calling x's the resolved variables, y the unresolved variables in a closure problem. And we are going to estimate them by using here as a surrogate dynamical system, a quantum system whose state is going to predict the closure terms. So think of it also in a version of so-called superparametrization that one sees sometimes in atmospheric dynamics, where now the surrogate model is actually a quantum mechanical sort of like data-driven learned model. Let me spare you the details, but the idea is similar to what we had before in data assimilation. The difference now being that the quantum system influences the classical system, whereas in data assimilation we didn't have that. We were only being influenced by the observations of the classical system. Here we're also predicting the closure fluxes to advance the state of the unresolved variables. But mechanistically it's the same. So I'm going to show you here one illustration of basically the example from Palmer, where we took the Lorentz 63 equations in the PCA basis. So these are ordered in order of decreasing explained variance. We discard the third equation, and then we treat the third coordinate as the closure term that we have to estimate. And this is showing basically a comparison between the true Lorentz 63 attractor, the prediction of this quantum mechanical closure, and the Gaussian closure. We can see we do have a rather good reconstruction of the attractor. As it turns out, we can reconstruct the attractor, in fact, in 3 dimensions, not just on the 2 coordinates. Whereas in the case of the Gaussian closure, because the third coordinate is effectively like a Toyn-Cos, it's like a random process, the structure is lost. But this method, in this simple, admittedly example, learns also the unresolved degree of freedom. It also captures the statistics. These are like the time correlation functions and histograms of the state vector component. I will end, I guess, and I'm happy again to talk about this in more detail offline, with some examples. This is like more recent work that we are trying to apply this methodology to closure of PDE systems, where now the difference is that the state space of the system is in itself a function space, like a PDE. So effectively what we end up doing, we're building, injecting, say, on a discretization grid of a PDE, we're injecting these quantum mechanical states, small quantum mechanical systems. Again, think of it as a super parametrization from, say, atmospheric modeling, whereas the surrogate models are quantum mechanical models localized in space. We've done this also in a way that takes into account symmetries. I don't have to talk dynamical symmetry. I don't have time to talk about this now, but since it came up yesterday, I'm just mentioning Briefly, I will skip, this was the shallow water equations. I will just leave this because I think for this group, maybe this is the more interesting example. This is work in progress, so there's a large number of caveats here. We're still working on this with my student David Freeman and postdoc Chris Vales and Joanna Slawinska over at Dartmouth. We are looking at like a closure of the cloud microphysics in an idealized cloud resolving model in 2D. And the results, these are very preliminary, but this is showing basically a comparison between the true model and the this surrogate, closure, quantum mechanical closure. This is the potential temperature at about 5 kilometers height, I think, where you can see these traveling waves that are being captured. So I will stop here, and I'm happy to take any questions.